So welcome to another session of Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but above all, we do also see and appreciate the beauty in the simpler problems. So today's problem comes from the MIT 2024 integration B semifinals problem number 2. Very interesting problem, which is the definite integral from x equals to 0 to x equals to infinity of x times e to the power negative 2x over 1 plus e to the power negative x. So before I jump into the solution to this problem, I'd like to thank our subscribers. Thank you so much for giving us your support. We don't take the support for granted. For our first-time visitors here at Everyday Mathematics, what we do is we go about on a run and look for seemingly harder problems, and we come back and share our version of the solution. To our repeating visitors who haven't gotten an opportunity to subscribe to our channel, we do really encourage you to consider subscribing to our channel. So how I would handle this problem first is I'll look at the denominator, and I would like to express that as a geometric progression problem. And in order to do that, I would tackle this plus as a negative. So we have this term 1 over 1 minus in bracket negative e to the power negative x as a progression, geometrical progression to infinity, with negative e to the power negative x as the common ratio, and the initial term being 1. And so I could express this as that series, and obviously keeping all the numerators as they are. And the next thing I would do is I would then go ahead and express this negative as negative 1 to the power k. And then I would multiply the e to the power negative 2x with the e to the power negative kx. And so you have this convenient term that is e to the power minus in bracket k plus 2x, while maintaining this negative 1 to the power k, right? Then what follows here is, so we have now swapping around, because really the integration of a summation of components is the same as the summation of the integral of independent components. So we can sum up the result of what we get from integrating each independent component. And since this negative 1 to the power k is a constant, we can just pull that out, and now our focus now is integrating from x equals to 0 to infinity x times e to the power negative in open bracket k plus 2x. And so as you can see here, we come up with first of all, let me indicate here, integration by parts, where we initially have 1 over k plus 2 negative times x e to the power negative k plus 2x. Now this comes from us considering initially that this is our u and this is our dv, such that uv is so v here is going to be this negative 1 over k plus 2 times e to the power negative k plus 2x. And then now we have minus, and this minus here, this becomes a plus 1 over k plus 2. And since now du here, because we need to get now v du, so we know our v, which is a product of this and that. But now du is a derivative of x, which is just going to be dx there. And so eventually now we, because when x is equals, or x tends to infinity, this exponential part tends to 0, right? And then when x is 0, this part here tends always equals to 0. So this time here, essentially the entire thing just tends to 0. Okay, then so we are left with now just the integral of negative the integral of e to the power k plus 2x, and then obviously the constants remain as we see. So going forward, we do now have another k plus 2 that emanates from integrating this, and this is arrived at as follows. So we have negative k 1 over k plus 2 e minus k plus 2x as the integral of this, and then the limits are shown here. When x tends to infinity, this part tends to 0, and then when x is 0, this part is 1. So we are left with now the summation of negative 1 to the power k over k plus 1 squared, multiplying this k plus 2, k plus 2. So this is where everything now starts being very interesting. So the first thing I would do is obviously I would just spell out the entire expression, and how we do that is first by assuming that, well, let k prime be equal to k plus 2, right, such that this tends to k prime, and this here tends to k prime minus 2, right? And when k is equals to 0, k prime equals to 2. And so we can now shuffle back k prime to k, so that's why we get this expression here. So just imagine k prime being what is k here. Now that's very interesting because this is the same as negative 1 of the power k over negative 1 to the power 2. Negative 1 to the power 2 is the same as positive 1. So negative 1 to the power k minus 2 is the same as negative 1 to the power k, right? And then we can now spell out everything here, and that is 1 over 2 squared when k is equals to 2, 1 over 3 squared when k equals to 3. Now because when k equals to 3, this is now going to be negative 1. There's a negative sign here. When k is equals to 4, since this is even, this becomes 1, so we have positive 1 plus 1 over 4 squared. And when k equals to 5, because this is a negative, we have minus 1 over 5 squared plus 1 over 6 squared minus, and so on. Now we can separate the odd from the even terms. And so we have 1 over 2 squared plus 1 over 4 squared plus 1 over 6 squared minus 1 over 3 squared. So in bracket here, 1 over 3 squared plus 1 over 5 squared, 1 over 7 squared, and so on and so on. If we pull a quarter out, this becomes 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on and so on. And this becomes 1 over 3 squared, so this just remains as it is. Then we can go ahead and now since we know that the summation of 1 over k squared from k equals to 1 to infinity is equals to pi squared over 6. This is a Bessel problem. This entire thing here becomes pi squared over 6 now times their quarter. So this is obviously taken care of. But this one here, now we have these odd terms. How do we solve that? So how we solve that, since we know that the even terms here amount to a quarter times the Bessel constant there, the Bessel problem constant. So we know this is the odd terms minus the value when k equals to 1. So in order to compensate for that, so we've added 1 here and then we've subtracted 1 on this other side. So what then happens is we have a quarter times pi squared over 6 and so on and so on. But now we know that this is the even terms, and the odd terms is simply the sum, the Bessel problem minus the even terms. So that's what we've done here. Pi over 6 minus pi squared over 6 minus pi squared over 24, because this is just the even terms. So in order to be left with the odd term, this is what you're going to do. And then we've kept the -1 there. And so just simplifying this further, pi squared over 24 from 4 times 6 here, and then here we have pi squared over 24. Since there's a negative and negative here, when you add these together, you get pi squared over 12. And then since we have pi squared over 6 here, we'll just keep the -6, and the minus and minus here amounts to a plus here. So pi squared over 12 minus pi squared over 6 is what we see here, and then when you perform that, this becomes negative pi squared over 12. So we have now this +1 minus pi squared over 12, and this is the final answer. So thank you so much for that attention. If you have any question, please leave your comments and questions on the comment section. If you have any other ideas on how to tackle this problem, we do welcome your suggestion. But it's been an absolute pleasure hanging out with you. Until next time, at Luca La